Good morning, everybody. Welcome to the Software Productivity and Sustainability track. Oops, gotta get that. So I'm gonna do, just try to continue the introductions briefly. So Ray has introduced me and Anshu. Rinka Gupta is also at Argonne National Lab. She's a research software engineer there, and David Rogers is in ORNL in the National Center for Computational Sciences, which is where the Summit and other systems are. We are all members of the Ideas Productivity Project, which I will tell you more about in a moment. I did want to go back here and point out just this slide 2 in all of our presentations is a license for reuse of this material if you ever want to do that, and a request for a citation if you ever wanted to cite it, and also acknowledgements from our sponsors. We are primarily supported here by the Exascale Computing Project, and so I do want to acknowledge their important support here. So the Ideas ECP project works with the Exascale Computing Project community to improve developer productivity and software sustainability. And we do that in a number of ways. We're trying to understand the methodologies that people are using to successfully improve their scientific software development practices and the workflows associated with that. We're trying to capture that information and make it available in other forms. We're trying to help people incrementally improve their software practices. We have something, a simple process we'll talk about called PSIP. We work to establish communities to get people talking together about policies, about other aspects of software development, and we do a lot of outreach. This is one of our outreach activities where we try to work with a broad range of people. We give a lot of tutorials. We have a monthly webinar series, a quarterly panel series, and we have a site called Better Scientific Software, which is a web resource for capturing information that you can go to at any time and look for information to help with software practices and related information. This is really a community resource that we've started it from our project, but we're interested in contributions from everybody. And so the idea here is if you have resources out on the web, books, other things, videos, whatever, that you find useful for software development and understanding how to improve your practices there, please let us know about it. And so there's opportunities to find things, opportunities to contribute, and we welcome participation on both sides. If you're interested in keeping track of us after this tutorial, we have a mailing list for ideas organized activities. That's things like our webinar series. And we do a lot of events at major scientific meetings like SciAm and supercomputing and other events that are related to software development, software sustainability, and things like that. And so this mailing list, low volume, announces things like that on a regular basis. And then the BSSW site has a simple monthly digest that comes out that highlights new items. We publish information about upcoming events there. We have blogs that we solicit there and other resources. Very soon we have the Better Scientific Software Fellowship, which is opening up for applications for the class of 2022. This is also a low volume mailing list, which you're welcome, and it's separate from the Ideas mailing list. So these are a couple ways to keep track of us in the future if you're interested. We do have some hands-on activities associated with the tutorial. We haven't had time in this session to build in work time on these, but you're welcome to do these on your own if you're interested. So the instructions are down at the tutorial website, which is the link down in the bottom. And I'll get to the tutorial website in a moment for some other things. The problem you may be familiar with is the same one you saw in the numerical libraries session. So we have worked with them to take simple code from that, implementing that model into the world of software engineering to think about it from a project perspective and how you could improve the code and some of the practices and things like that. We do, as I said before we really got started, we do want to interact with you. So we find these tutorials most interesting if you ask questions and share experiences. So we would please encourage you to use the Slack channel, the Track 7 Software Productivity channel, to ask questions at any time. We will try to stop for questions during our presentations as time permits. But if you put something in the chat, there will be, anybody who's not speaking from our team is likely to be paying attention to the chat. They may be able to answer. And historically, in situations like this, we've had some interesting conversations going on in the chat alongside the presentation. And if you don't get your question answered, please follow up with us afterwards. We're very interested in keeping up with folks afterwards. We have an email address that's listed at the bottom of the slide that you can contact us at. And also, if you do choose to work on the hands-on activities, submit pull requests or issues in the repository, and we'll take a look at those and give you feedback there. So that is just a very quick introduction. And now I'm going to move on to the overview presentation. And this is really to sort of set the stage for the rest of the track today and talk to you about some of the things you'll be hearing about later in the day. So a fundamental message that we want to convey here is that science through computing is at best as credible as the software that produces it. And that's really, I think for any scientist, that should be the fundamental concern about the quality of the software that you're producing and using. And so it's easy to say, but it gets more and more challenging as time goes on. We're in kind of a positive feedback loop, which is good in many respects. We've been able to produce more complex codes and run more sophisticated simulations and analyses due to better computing capabilities, better algorithms, and things like that. But that feeds a desire for more of these things, bigger hardware, which turns out to be more complex hardware, more complex algorithms, coupled physics, all kinds of things like that. And we have gotten into a situation by and large in our community where you really need a variety of expertise to deal with all the different moving parts in a large complex simulation code. And really the only way to deal with these things is to think about separation of concerns. So you need people with different backgrounds, you need to use separation of the concerns in the code and things like that. And this means a team of people have to be involved in practice in the development of most scientific software applications these days. And it's really hard to work on a large complex software package with a bunch of people with different backgrounds and things like that without some set of rules, some basic software engineering processes, keep everybody on the same page to help ensure that everybody can produce and understand code that is at some level consistent. And then, as I said, we've been getting more and more capable hardware, but that has also been more complicated hardware. And that influences the complexity of the code that we have to produce to run well on it and things like that. And so that further complicates the software development challenges, the portability challenges, and the sustainability challenges, because we want to make sure that the software we're developing can live from one generation of hardware to the next and can be adapted to as changes are necessary. So we need to invest in flexible design and, once again, a robust software engineering process so that you can take the code through these changes over time. There's a lot of challenges in scientific software development today. Some of them are technical, some of them are sociological. On the technical side, we've got complex systems, we've got lots of software here. All parts of this, the model that you're coding to and the software itself can be topics of research at any given moment. The requirements will change throughout the life cycle as your understanding grows of the problem, as the situation changes, things like that. We're almost always working with floating point based computations, and that has its own challenges, and especially in the verification stage. And we're trying to simulate the real world, and the real world is messy. And as we do a better job of trying to simulate the real world, the software gets messier as a consequence as well. And finally, there's this increasing architectural diversity that I mentioned before that provides a lot of technical challenges, especially recently. On the sociological side, competing priorities and incentives. So as you may appreciate, especially those folks here who are a little further along in their career, it can be hard to get recognized for software development as opposed to science publications and things like that. Producing a really good software package is not always enough, you know, for those who are being evaluated for tenure or promotion or things like that. And sponsors also often care more about scientific publications than the software that is behind them. And so something else we're trying to do in the Ideas Project is to help feed a culture change in the larger community, sponsors and within the community, to help improve the recognition of the importance of software so that we can do a better job of balancing software development and maintenance with the research and things like that we need to go on. We also all know about limited resources. You have to make choices. You can't do everything you want. And then this need for teams with different backgrounds can be a challenge as well. You need different kinds of experience these days on your team in order to be successful, but that can also exacerbate the challenges of communicating, having a common language to talk about the problem and the software and things like that. So there's a lot of challenges that we have to deal with. And we've seen many cases where software challenges have led to high-profile failures. One from back in the 1980s was a computer-controlled radiation therapy system called Therac-25, a combination of poor software design, poor development practices, and ineffective testing practices allowed flaws to get into this product, which allowed at least 6 cases of substantial radiation overdoses to be administered to patients. At least 3 of these that we know of were fatal. And then more recently, just in 1999, the Mars Climate Orbiter made an incorrect trajectory adjustment, which caused the loss of the orbiter as it was supposed to enter Martian orbit. And the investigation showed that there was a discrepancy in the units between 2 different software components. One component didn't follow the specifications that had been established, and obviously there wasn't enough testing at the interface to detect that one of those components wasn't properly following the specification. Concerns were actually raised earlier in the mission, but they were ignored because they weren't properly documented. And so that's quite unfortunate, but it is also, especially in a large organization like NASA JPL, you know, there's a process that's in place to report issues and things like that. And if you just do it on a casual basis, it's easy for issues to get lost. These are just a couple of examples of high consequence software failures. You can probably point to 3 or 4 others that you've heard of. And really, we want to avoid a lot of these things, but there's also oftentimes a lot more subtle situations in science. And this is one that comes from Anshu Dubey's experience with the Flash astrophysics code. So back in 2005, the Flash team was offered an opportunity to get dedicated access to one of the biggest machines in the world at that time, a Blue Gene L. They had a short time to prepare, so they had just a month to get ready for this major run. So they did some quick and dirty development in their code of a particle tracking capability, and it turned out that there was an error in the code that they implemented, which resulted in duplicate tags due to a round-off error, which is a floating point problem, referring back to the couple slides ago. And it took them 6 months to process the results with some tools they had to develop to correctly back out the issues due to these errors in the software. And the real point to make here is that Flash had a software process in place. The software was tested regularly. This is one case where their full testing process couldn't be applied because of time constraints. And this is something that's not uncommon in science. We have paper deadlines, we have to get results for a sponsor, we have a unique window to access a resource and things like that. And so what we end up doing is developing technical debt. You may have heard this term. Basically, technical debt is the implied cost of additional rework, due to choosing a simple, limited solution instead of taking a better approach that would take longer. So technical debt is very much like monetary debt. The more you accumulate in your code, the harder it is to pay off. So it increases the cost of maintenance over time. Parts of the software may become unusable over time. They're inadequately verified, so you may get questionable results. All the fact that this is not done or documented as well as it could be increases the ramp up time for new developers. And so overall, technical debt reduces your software productivity as well as your scientific productivity in the long run. And what we're aiming here is to think about software productivity and enhancing your software productivity as a tool to enhance your scientific productivity. They really go hand in hand. So another thing to recognize is that scientific facilities, computing facilities, provide very valuable resources. Every major supercomputer that's out there these days costs more than $100 million, and they cost millions of dollars a year to operate. So anybody who gets a significant allocation on a large supercomputer, the allocations themselves can be worth literally millions of dollars. And if you are a commercial company, you'd actually have to pay that money to get access to the system. You're typically getting access to these systems because you're publishing your research results openly. And so even if you don't have to pay the dollars, you have to spend time and effort to get the allocation. You have to write an insight proposal or some other proposal and things like that. So, sponsors have a natural concern. Are you being a good steward of the resources that they're giving you? And your concern should be similar. Are you getting the most science that you can out of the runs that you're doing on the computer? So your scientific productivity to demonstrate to your sponsors that you're a good citizen. But it's also obviously to your own benefit to have good scientific productivity. Excuse me. So really, the message here is that good scientific process requires good software practices, and that good software practices increase scientific productivity. And at the same time, good software practices also increase software sustainability, so a longer term thinking about your software. And we find as many software packages live for quite a while. I've worked with packages that are now 30 and 40 years old, literally. They haven't been static all this time, they've evolved, but these are long-lived software packages. And so paying attention to the sustainability of the software and having it structured in a way that can be sustained and maintained over that kind of time frame also increases your scientific productivity, because you don't have to go in and reinvent a lot of things. So what are good software practices? That's kind of fundamentally what we're about at some level. Well, I hate to say it, but there's no fixed, universally agreed set of best practices for scientific software. The specifics of what's appropriate will depend on your software, how it's used, and the team. And you can think about this in a graduated way. If you're doing just some software for your own purposes and you're not sharing it with anybody, that's sort of one level. If you have a small team and you're just publishing some papers, that's another level. If you're producing a package that you're distributing to many people and you have hundreds or even thousands of users, that's another level that you need to think about. And so let's just look in general at some of the recommendations that folks in the community have made from several different perspectives about good software practices. So the first one comes from a paper by Greg Wilson and others in 2014. So their paper is titled Best Practices for Scientific Computing. And I won't go into these in detail for lack of time, but I encourage you to go back and look through this in the next few slides and think about how you might have, whether your projects are implementing some of these best practices and what might benefit you to think about implementing in the future. So write programs for people, not computers. Let the computer do the work. So that's script things, and if you have to repeat things, you know, try to capture that information so you don't have to recreate it out of your mind. Automate workflows and things like that. Make incremental changes rather than huge adiabatic changes. Going back to the letting the computer do the work. Don't repeat yourself, right? If you have one authoritative source of data, don't copy code, modularize it, reuse code, things like that. And plan for mistakes. Test, add assertions to your code, things like that. If you get bugs, turn them into test cases. More of these practices that they recommend: optimize the software only after it works correctly. That's really important. So it's easy to say, to look at something and say, oh, if I just made this optimization, yeah, I know it would be faster, but it's really useful to get it correct first so you can be absolutely confident. And then when you make changes to optimize things, maybe the compiler has problems or things like that. You have to really be careful when you're making optimizations. Document the design and purpose of the code, not the mechanics. So, if you have a code that says the comment says set A equal to B, and the next statement is A equal B, that's not very informative. What are A? What are B? Why are you doing this? Things like that. Think about refactoring your code as you go along to improve it and make it better and more natural for as the code evolves. And embed documentation with the software, because that's the easiest way to find it and encourage people to keep it up. And then collaborate. And collaboration here is not just people working together to develop software, but also doing code reviews of each other's code, pair programming, getting more eyeballs looking over code so that more people understand it, can pick up errors and things like that, and also using issue tracking tools and things like that, so that you're collaborating also even with your users about identifying and fixing errors. So these folks in 2017, a lot of the same people realized that maybe best practices is too high a bar. So they did something called good enough practices. And this is a bit more elaborate, and I am going to skip over these a little more, but they have points on data management, on software, how to write manuscripts, more about collaboration, how to organize the project, keeping track of changes, things like version control, and things like that. So there's a lot of suggestions here to dig into. And then there's another thing I'd like you to consider, which is the Linux Foundation Core Infrastructure Initiative. They have a badging program. There's a URL for it there. This is not specifically intended for scientific software like the other two are, but it is a very extensive set of best practices that will benefit almost any software packages. This badging scheme has 3 levels: passing, gold, and silver. There's a combination of things that you must have and things that you should have depending on the different levels. And this is worth looking at to get some ideas. And here I've greatly simplified, because this is a very extensive set of criteria. Pretty much all these criteria, actually, it's interesting, they have links to justify why they're making that recommendation, which is something, even if you don't necessarily want to adopt this particular list, you can go and use it to get more information for arguments as to why these things are good. But they have requirements in change control, in reporting and bug reporting, quality control checks. Security is a very important thing that's even more and more applying to scientific software, especially as we get into workflows and more complicated coupled codes and bringing in data from outside. And so the message with all of these is these are really good examples of things to think about. As I said, they need to be adapted for what will work well for your project and what your project needs. And so A lot of these things out there are from the more general software engineering community, and they don't necessarily speak to scientific software developers directly. That doesn't mean we should ignore everything that's out there in the software engineering experience, because there's a great deal of it. What you should think about when you're reading software engineering suggestions from other, outside of scientific software, and it doesn't sound quite right, is what in there can we adapt? What would help what within this approach that they're talking about would help my project do a better job? And so you can talk to colleagues who may have adopted some of these techniques or face some of the same challenges that you do. There's always more than one way to skin a cat here. And in the end, you might find that some things don't work very well. So don't be afraid to try something out. And if it's really not working for you, go back and say, okay, that's not the solution we're looking for. Let's try something else, or let's step back a little bit. Don't be afraid to experiment. So another question that's often asked is, how much time or effort should I spend on software engineering? And I think the basic message, the basic practical message here is your project should include just enough software engineering so that you can meet both your short-term goals and your longer-term scientific goals effectively. And once again, this is going to vary a lot depending on your situation. It's nice to think about, doing everything to the max with good software engineering practices, but that's not necessarily, as a scientist, where the best way to spend your time, and that's what we're looking at here. One of the things we do recommend is a process of continual incremental process improvement. So really what we want to achieve is something like this graph on the right here. So you have, some old process, which is depicted in red, and as you make progress, there's a certain cost to it, and you continue to make progress. And what you're trying to do is look for changes to your software development practices that will bend this curve down. So you want to look something more like the green curve, right, where you can make progress at a lower cost. Now that's typically going to require a bit of an upfront investment, but then you're looking for a payoff. So the way we recommend to think about this is to identify your team's pain points in your software development processes and pick one thing to set a goal to improve. Target process and behaviors, not just tasks that need to be done, and pick something that you can address in a few months so that you'll get a benefit, and you can say, yeah, that, get a bit of a good feeling from it. So agree on a plan. How do you decide when you're done with this work, and what are some of the intermediate markers of progress, and write them down. And this becomes your plan. It's a progress tracking card. And then you work to the plan over a few months with your team, and you track your progress. Have you met this first milestone? Have you met the second milestone? Have you achieved what you call done, right? And when you're done, celebrate. That's a great thing. You've improved your software development processes, and then you can pick a new pain point and improve the next issue. We call this productivity and sustainability improvement planning. There's a link there that you can follow to learn more information. It's really simple, but it's a very powerful concept. A lot of the things you'll find in software engineering are simple, but their simplicity is part of their power. So about today's tutorial, there's a lot of useful topics that we could try to cover to help you improve your scientific software development processes. We're going to focus on a few where we find that the software engineering advice in the wild typically doesn't address the needs of scientific software. So we're going to look a little bit at project management. We're going to look at collaboration around software development, software design, testing, refactoring, continuous integration, and we'll talk about reproducibility. So there's a lot of other topics, like I said, and we're happy to talk with you about those, but we're not going to have content on those. So the agenda we have today, we'll hear about agile methodologies and something about Git workflows, which is a collaboration tool for software development teams. We'll hear about software design, reproducibility, come back a little bit with more on agile methods. And then after a lunch break, we'll have a series of talks about testing and continuous integration. and then refactoring. We have just a little bit of time at the end reserved for Q&A, but as I've said, please ask questions at any time using the chat, Slack, or maybe people are using Zoom. I think we'd like to move things to the Slack if possible, because that's more persistent. So this is the outline for the day, and I encourage you to, so the presentations for today and the agenda, and also this link to the tutorial website are all in the box folder that you all have access to. But the tutorial website, if you go down into the ATPESC page, we'll have all this information. This is publicly available and it'll be there in perpetuity. So if you lose access to your box account or things like that, this will continue to be out there. The slides are up on Figshare. There's a link there. And this also has the hands-on instructions. And so with that, I'm going to introduce Rinku Gupta, who's going to talk about Agile methodologies. And we would be happy to also take any questions as we go along. Please remember that. Thank you.